Welcome, video example 7, unit 2, chemistry 1B. Here we're going to calculate delta G at non-standard conditions. Okay, so in this instance, we are being asked to calculate delta G at 298 Kelvin for the Haber process. We are given the standard reaction. So this here is the standard reaction. So delta G at 25 degrees standard is minus 33.3 kilojoules. And then we're given some conditions. So the reaction mixture, we've got some concentrations. Now remember that gases use partial pressures. So these are partial pressure concentrations. And our first step, because essentially what we want to do, we want to use this equation, delta G is equal to delta G standard plus RT ln natural log Q. Okay, so that's what we're after. So we need to first calculate Q, which is easy enough to do because you know how to do equilibrium conditions. Okay, so setting up the reaction quotient, we take the products squared because of the coefficient of 2 here. And then we take the, at the bottom of the quotient, we have the partial pressure of nitrogen multiplied by, there's a multiplication sign there, the partial pressure of hydrogen cubed because the coefficient of hydrogen is 3. Okay, so then we can plug the values in that we have. So the partial pressure of ammonia is half an atmosphere and we square that. The partial pressure of nitrogen is 1. And the partial pressure of hydrogen is 3, which we raise to the third power. And we work out that the reaction quotient ends up being this value over here. Right, now we can continue and plug the value of Q into this equation, plus all the other factors that we have. So we know that delta G standard is equal to minus 33.3 kilojoules. Okay. And we know that we have the gas constant, we have the temperature. Temperature is 298 Kelvin, 25 degrees is 298 Kelvin. We must convert to Kelvin always. And we have the value of Q as 9.3 times 10 to the minus 3 from the previous calculation. So we can then do the calculation and end up with a value for delta G at non-standard conditions, so the ones, and we see that the value, it works out to negative 44.9, which is higher than the standard value, see? So that means that at standard conditions, okay, all gases are at 1 atmosphere pressure. But if we change them in any way, okay, so we've changed them now to 3 atmospheres of hydrogen and half an atmosphere of ammonia, we find that we can actually drive the equation to the right and produce more products, okay? Because that means the delta G is going to be more negative. So in this case, with this particular set of concentration values that were given here, it indicates that we have this driving force to form ammonia. And we obviously see that the partial pressure of the reactants is much larger than the partial pressure of the products, and obviously then we have a drive to form. So in a sense, we are proving by doing a calculation Le Chatelier's principle.